All right, in this session we'll be looking at modeling in the electrical and mechanical systems. All right, so the key thing here is that whether it's the electrical systems or mechanical systems or electromechanical systems, the key factor will be that those fundamental principles of electrical and circuit analysis, electrical principles, like Kirchhoff's laws for Kirchhoff's current law, Kirchhoff's voltage law, or and from a mechanical point of view, flow rates, forces, friction, all that kind of stuff, all that kind of fundamental things related to those two specific areas of electrical and mechanical are very, very important that you start looking back over those things and are very strong in those things. Okay, so let's start off with some relationships to simple circuits. Now, when you're analyzing circuits, it doesn't matter whether you know, what kind of form of circuit analysis you do. Again, it's really up to you. If you want to do mesh analysis, loop analysis, nodal analysis, whatever you want to do, as long as you demonstrate, that's the key thing, mathematically demonstrate what you're doing, then there's not a problem. So here we have a very, very straightforward LRC circuit or an RLC circuit, resistor, inductor, and capacitor. And what we're going to do is go about modeling what's occurring in this particular circuit. So determine, in particular, the transfer function relating the capacitor voltage, VC, voltage capacitor, as a function of S, a function of frequency, to the input voltage, V of S. So that's the output over the input, which equals VC of S divided by V of S, and assume zero initial conditions. So as we said, an RLC circuit, nothing startling about that. So as we go through, a couple of things. Initial conditions are very, very important. So when you are doing problems, you should state what your assumptions are. And one of them, unless you're told, because sometimes the initial conditions aren't zero, they could be a particular value. Keep in mind that you should be stating something about the initial conditions, because that will be significant in the long run. So method one, we're going to use differential equations to determine the transfer function. So if we use Kirchhoff's voltage law to obtain the integral differential equation, which just basically means you've got differentials and you've got integrals in it. So as you cycle through that circuit, you know that from Kirchhoff's laws that the total voltage equals the sum of the voltage drops across each of the components. So we've got an inductor, so voltage drop across that, the voltage drop across the resistor, and the voltage drop across the capacitor. So going back to fundamentals, as I said beforehand, you've got to know your fundamentals. So by basic definition, voltage of your inductor is just the inductance multiplied by the change in current. The resistor is the resistance multiplied by the current. And for the capacitor, as you can see there, that's how we go about calculating. So 1 over the capacitance multiplied by that integral equals our overall voltage of our system. So what we're going to do here is make sure that we're working in you know, one set of variables, because we're looking for a change in one voltage, particularly the capacitance voltage, to the overall voltage. So here, what we're going to do is use some of our basic definitions. We know by definition that the current is equal to the change in charge flow over time. So what we can do is go through and substitute in that for our current, do some simplification to end up with this expression, which is the second order differential equation. So if we look closely now for the capacitor, we know that the voltage across the capacitor is equal to 1 divided by the capacitance times the charge that's flowing. So basically we rearrange that equation, and we're able to drop that into this equation now, because really we want, as we can see, some relationship between the voltage overall and the voltage across the capacitor. So we're getting closer to the relationship that we want. So the key thing is to keep checking that we've got the expression that we're looking for. So again, another second order DE, but now, instead of being in charge, see how that's in terms of charges, Qs. This is now in terms of, and charges and voltage, source voltage. And now this is, again, this is a differential, second order differential equation, but now the variables are such that we're talking about the voltage across the capacitor in relationship, comparing it to the total voltage. So all good. Now again, just reminding ourselves that as we take the Laplace transform, that we're going to assume zero initial conditions, otherwise we have to evaluate things at zero and add them in. So here You take the Laplace transform. Again, you just take out any constants. They're all constants, they're just numbers. So take out the constants and then concentrate on. So why I do this is to make sure that you're concentrating just on the bit that you need to concentrate on. So do that. You've got to look up your tables, and you'll see very, very quickly that they are your Laplace transforms for each of those values. Then you're rearranging, and the relationship you want, as we said, is the change in voltage across the capacitor over the source voltage. So now we have this equation 1. So this is a transfer function. VC, the voltage across the capacitor, over the voltage supply equals this interesting relationship here relating the inductance, the capacitance, and the resistance in particular. So that's our block diagram. Now, the equation, as we said, that this part here is the output over the input. So that's called transfer function. And this transfer function represents a relationship describing the dynamics of the system under considerations. And since we've got S's, as soon as you see an S, that's the frequency domain. We can determine information, energy, input signals. Now the denominator, when we set that to 0, and this is a basic mathematical principle, we call that the characteristic equation. So that equation there, this quadratic that we see on the denominator, anything on the denominator, we equate it to 0, that becomes a characteristic equation, which tells us characteristically about what's going on. So that you'll see that we'll bump into the characteristic equation a lot. And when we set that to 0, those roots of the equation will determine the character of the time response. Now the roots of the characteristic equation are called the poles, and the roots of the numerator are called the zeros. So the roots of that are zeros, the roots of that are poles. And we'll talk more about zero and poles as we cycle through a while. And these are critical, terms or critical frequencies. And at the poles, the transfer function becomes infinite, whereas at the zeros, the transfer function tends towards 0, becomes 0. The complex frequency S-plane plot of the poles and zeros graphically portrays the character of the natural transient response of the system. We'll talk, as we go through different topics, we'll talk more about that as well. So that was method 1. So method 2 is from the circuit diagram to the transfer function. So in this way, we can redraw the original network showing all the variables, particularly the time variables, in the time domain. So V of t, voltage with relationship to time, that's the overall voltage, source voltage. I, the current as a function of time, and the voltage across the capacitor as a function of time. As Laplace transforms V of S, I of S, and the C of S in the frequency domain. So replace the component values with their impedance. So we go through, and here's for our resistor, here's for our inductor and capacitor. And these are all just from definition. So it's just fundamental knowledge. Take the Laplace transforms of those things, and then when we do that, there will be the forms for the resistor, the inductor, and the capacitor. And then we can find the impedance. So just rearrange that. Again, we're talking about impedance because it is an AC circuit. So rearrange that and get them in that form. Now redraw your diagram. Okay, there's our original circuit diagram now being redrawn. So that's good. And then we do our Kirchhoff's relationships and look at the sum of the voltages. So we can get this expression. And then we know that the current flowing through the circuit equals S times the capacitance times the voltage across the capacitor. Plug that in, and again, we can get a general expression to find out the ratio or the transfer function. And oh, surprise, surprise, we're going to end up with exactly the same transfer function. So we've got two methods. You can adopt either one. It doesn't really matter. And you can use any, again, on top of that, you can use any type of circuit analysis that you're comfortable with, provided you can support it by the proper mathematics, then there shouldn't be a problem. All right, so that's an electrical system. What about a mechanical system? So here we're going to use the differential equation to determine the transfer function. We're looking for a transfer function, so it's x of s divided by f of s. So we've got something about the distance or displacement over the force that's occurring in this system. Now keep in mind that these systems are really analogies. So you've got this large mass, and basically you've got some motion of some sort that's allowing it to move backwards in forces, back and forward. And also here you have some dampening force of some sort. So there's something that's stopping that from, just vibrating madly. Also, the general direction of the motion is in this direction, and the force being applied is in that direction for whatever reason. And it's tethered to some quite solid object. So remember, this is an analogy or a representation of the system. Keep that in mind. So here, this might be this could be an air conditioning unit. So what happens is that some air conditioning units are set up on springs so that when the motor kicks in, they vibrate a bit. So the point of the matter is that some of that vibration is able to be taken out by set of springs, little springs that are under each foot, and also there might be some dampening effect occurring as well. So again, keep in mind that this is a representation. As I say, it could be a air conditioning unit on top of a roof or something like that. So again, by basic definitions, from our fundamental knowledge of springs, dampers and masses, that's basically our expressions that we use for force over time. Conditions and assumptions, as I said, always state what your conditions, your assumptions are. So we're going to assume that the mass is traveling toward the right, and we know that from that expression there. We've been told that, so that's a good thing just to state that to make sure that it's understood, that you're working with that. And the point of that is because that will help you with your free body diagram, and particularly in directions, because if it's that way, then that's the positive direction. So a sign convention is going to say that anything value that you're measuring in that direction is positive. So as it goes back in the other direction, that must be a negative distance or displacement that's occurring. So that's exceptionally important. Now, owing to number one, only the applied force points to the right, and the other forces impede motion and act in the opposite direction. That's where we're able to generate a free body diagram. So in other words, again, if I pull on this thing, the force that we're talking about, as I say, you turn it on, so therefore the electrical current goes through, the motor kicks in, so the motor is producing that force which is making the air conditioner vibrate towards the right. So all these other things are going to restrict it, so they must be opposite directions, so there will be negative values that are occurring when we calculate a force for this particular thing and a force for this particular thing, then they will be negative. There is a frictionless surface, otherwise we would need to take weight into account, but also resolve moving horizontal forces. So sometimes, as a mathematical problem, you can do that, and other times you will not be able to do that because you'll need to take friction into account because it's exceptionally important. So it just depends on the problem, and then assume initial conditions. So in other words, when we're starting to analyze the system, it hasn't been turned on, so nothing is occurring. Here's your free body diagram. Again, as you can see, it's probably a good idea somewhere to state positive direction. But the reality is that in some ways it is implied, because we've got this is saying, hey, listen, this is the direction of motion. That's the direction the force is being applied, which causes the disturbance. So therefore, then anything else in the other direction these must be negative values when we go to calculate them. We've been able to write them in fundamental forces. So we're talking about forces, balancing out forces. So all of these are forces balanced out against this force here. Taking a Laplace transform, so again, very, very fundamental. We end up with these expressions, and then we can transform our free body diagram into the frequency response. We can write down our representative differential equation. Again, it's a second order equation. You can see we've got a squared term there. There's our individual spring, damper, and our mass has to equal the overall force. So taking a Laplace transform, assuming initial conditions. Again, otherwise we have to put in those initial conditions. We can rearrange this now to get our transfer function. And remember, our transfer function we wanted was the displacement, x of s, divided by the forces. So that's f of s. So we end up with this expression. So if we're going to draw a block diagram, that's our transfer function in algebraic form, and that's our transfer function in block form. So a nice easy block, but that's essentially what we're doing. And a little bit later on we'll do block diagrams, and there's block diagram or block algebra, and the reality is what you're trying to do is to take those blocks and get them down to a single block like this. So the simplification you'll always end up with this type of thing. So that's a transfer function defined as a block diagram. Okay, so method 2, from the diagram to the transfer function. Here's our original diagram. We go straight to our Laplace transforms. We're able to get those in very, very quickly from our fundamentals or fundamental knowledge of springs, dampers, and masses. They're our fundamental expressions. Rearrange those, defining the impedance, just like we did for the electrical, so exactly the same method. Then our free body diagram will look like that. So there, finally, we can rearrange that now to find our transfer function. So no big surprise, this method will give us exactly the same transfer function. All right, good. So we can have translationary mechanical systems, so things moving left to right, up and down, but also things rotate. So in a rotational mechanical system, you can also do transfer functions. So this is the type of situation. This particular thing here, as you can see, you've got some bearings on either side. You've got torsion occurring. So this could be the rotor in an electric engine. So again, even though it's an electrical engine, the point of the matter is it does have rotational mechanics involved with it. So the reality here is that we're going to find the transfer function of θ2 divided by T of S for the following rotational system. Now the rod is supported by bearings at either end and is undergoing torsion, so a torque. So therefore we have to look at torque. It's a turning force is applied at the left and the displacement is measured at the right. So here's our physical system. So we've got a whole range of variables. We've got angles occurring. We've got some friction, but we're going to ignore friction in this case. So, okay. Schematic of our physical direct particular system. So we can directly start to analyze this now to say, hey, listen, really what we've got is some dampening effects that are occurring. We've got some turning here. We've got some, basic expansion occurring left and right, damping down this end as well. So we start to analyze our system, which, as I said, could be electrical motor kicking in, that type of thing. And again, our assumptions, always state our conditions and assumptions. We've got 2 degrees of freedom resulting in each inertia can be rotated while the other is held stationary. So that's really the key to the problem. What we're going to do is start saying, hey, listen, if we hold this stationary and this twists and turns and bobs backwards and forwards, what does this do in relationship to that? Then we're going to hold this steady for argument's sake, and let's see what happens when this thing bobs and turns and bubbles backwards and forwards. So what we can do is to start to consider the torques on J1 if J2 is held constant or stationary. So what we said was the torques on J1, so this part of the equipment, J1, we're going to hold J2 stationary, hold it stationary, and see what happens when this twists and turns and moves backwards and forwards. So again, using our basic definitions, we've got a mass, a damper, and a spring. So we've got a mass, a damper, and a spring. That's how we're able to define our system from our fundamentals. Take the Laplace transforms, get those, and then probably a good idea is to draw diagrams are very, very important. So if we looked at it from a particular end, then we would see that this is what's occurring. We've got our J1, and we can see that it's starting to move in that direction. These are the directions that tensions and torques would occur in, and where movement would be occurring. So that always is a very important diagram. And then if we consider the torques on J1, if J1 is held stationary and J2 is rotated, in other words, the motion is only due to J2. So we look at our spring, take the Laplace transform, and then again, diagrammatically, we can analyze that from that particular perspective of holding the J1 stationary and J2 is rotating. And then again, if we go through and combine these effects, because overall that's what's occurring. We're looking at, as a system, we looked at individual components and looking at what happens when we hold that part stationary and the motion that occurs on that other one, and the interactions that occur if we hold the other one stationary and see what happens there. So we combine all those things, and then we consider our torques. So we go through and we're able to basically generate our expression for T of S. And then if we now go through the process again, but hold J1 stationary and see what happens to J2. So exactly the same idea. We've still got a mass, the inertial mass. We've still got a damper occurring, and we've still got a spring. Keeping in mind, we're looking at from the orientation in relationship to holding J1 stationary and see what happens when J2 moves. So we do the Laplace transforms of those particular quantities for our inertial mass, our damper and spring. and then again do our diagrams from the perspective of that particular orientation. Also consider the talks on J2. If J2, hold it stationary, and what happens to J1? Do your Laplace transform. There's your little diagram. Then basically combine all that information, because that's how we're going to go about generating our expression. So now we've generated a second expression by considering what happens to that J2 and J1 under those conditions. We can define the transfer function, so we rearrange that expression so to get that, and then we can substitute this now back into the other expression. And as you can see, ultimately we end up with the relationship or the transfer function that we're interested in, the output over the input. So we're interested, originally what we were asked to do, to find out what happens to that θ2 value, J2, divided by the overall T, the tension or torque that's occurring in the whole system. So as you can see, pretty much that's then the relationship that we're interested in, and are able to define that particular transfer function. Now we can also define another transfer function, for argument's sake, of θ1 over T of S. It just depends what you're concentrating on. Here you're asked to do θ2 over T of S. So keep that in mind. So now we can analyze that in the frequency domain and define some of the processes that are going on and the effects that that might have on that particular device. Also, so that's the analog or continuous focus, if you like, and then the digital focus for transfer functions of a sample data set, which just simply means we're talking about digital systems. We've discussed the Z transform previously. So here, these are our particular systems that we can have. We can have a continuous system, a sampled input, and sample input and output. So now in dealing with that, if we consider the continuous, if the input is sampled as shown in the figure, the above the output is still a continuous signal. It's still going to be continuous. And then, however, we are contented with determining the output at sampling instances and not in between, then the representation of the sample is greatly simplified, and basically you end up with the sample input and output. Now, an ideal sampler is not dependent upon the sampling waveform characteristics. So again, this sort of the highly mathematical part, but again, just bear with it and just follow it through. So you end up by able to define these type of expressions to ultimately get you to a transfer function. The transfer function, remember, is the output over the input. So you're able to define these types of output and input functions. Then ultimately the Z transform is defined as this particular summing over the whole K instance of 0 to infinity. And there's your Z transform. And remember, you're talking about sampling time. So in a general sense, that's KT, whatever the sampling time, the sampling interval is, or the sampling rate. They're all the same terms. So if we do that, then ultimately what you can do is we can mathematically go through, and as we go through, as I say, the key thing is what we want to do is get the application of these things. So as we go through and take our limits, etc., you're going to find that the transfer function will ultimately be just like for the analog system, the output over the input. So when we do that, we can end up with this expression. And this is a very important result, as it demonstrates the transform of the sampled output is the product of the transform of the sampled input and the pulse transfer function. Okay, now recall that although the output of the system is a continuous function, we had to make an assumption of a sampled input in order to arrive at this result. So one strategy to determine the pulse transfer is to commence by finding G of T and then use the partial fraction table of Z and S transforms to find G of Z. All right, as I say, that's the mathematical background. If you tend to find that kind of stuff gobbledygookly, don't worry about it. Let's go and have a look at an example and let's put it to the practice. But we have to give you that background mathematical theory as well. So here, this example, we're given a 0 order hold in cascade with this particular function here. G1 of S is S plus 2 over S plus 1. Or since they're cascaded, it means that they're going to run onto each other, they're connected directly, so therefore then we can now define this other function, G of S, which is made up of those two cascaded, the 0 order hold and this particular G1 function. Find the sample data transfer function, G of Z, at the sampling time, sampling rate, timing interval, all those kind of expressions, is T equals 0.5 seconds. So, okay, So we're going to start with that cascaded system. Now, the form of G of S presents a common occurrence in digital control systems. Namely, what you do is you have a transfer function in cascade with a 0-order hold. Now, remember, there are high-order holds, but we're just going to concentrate for an introductory unit. We're just going to concentrate on 0-order holds. But it'll be exactly the same process. It just means that these functions would be of a different form, slightly different. Now, we can develop a general solution to this category by a problem by moving the S in the denominator of the 0-order hold to the G1 of S, which basically means that we start off with our original configuration, the cascading, take it across, and then we can use that to find our Z transform. Go through and do your Z transform of each term. There's no common terms to take out. So just go through, follow your process, looking up your tables as you go through. So when you do that, basically you'll find we're in this form now. So G of Z is equal to this. So we've got to take the Z transform of this bit here and evaluating it at our particular T value. Remember, that's 0.5. Okay, now concentrating on the second term, we will need to begin by finding the impulse response or the inverse Laplace transform of G2 of S to find G2 of Z. So okay, now generate the partial fraction first. So if you look up here, we're going to concentrate on this term here. Okay, so we're going to find the Laplace transform of that, evaluate it at T, which is 0.5 in our case, then take the Z transform, and then we're going to be coming back to that expression. So we go through, as you can see, I do every line just to labor the point, but that's our function. Again, oh, hang on, remember, we're going to do partial fractions. So the first thing we're going to do is check to see if it's a proper fraction. So we know that as long as the highest order term in the numerator, it's S, so it's S to the 1. And on the bottom, if I multiply that through, there'll be S squared plus S. So therefore, the highest power of the particular expression in the denominator is higher than the one in the numerator. So therefore, then that's what we call a proper fraction. So we don't have to do any of that nasty polynomial division. So again, we're going to write that as a partial fraction. So that's S plus 2 over S into S plus 1 becomes A over S plus B over S plus 1. Go through, and again, we're going to form a common denominator through the normal processes. So now we have the same denominator, since we've got a common denominator, and we're going to be looking at assigning, evaluating the coefficients for the numerator against the coefficients of the numerator on the right-hand side, for those on the left-hand side. So when we do that, we can see that our S1 is 1 equals A plus B, so we can get an expression for that. Our S0 is, straight away we get A equals 2, so we can plug those numbers in, and straight away we can find that A equals 2 and B equals -1. So we go back, put that in a partial fraction. So our partial fraction is basically 2 over S minus 1 over S plus 1. So take the Laplace transform, we've done that. Yes, we can take out a common factor of 2 there, look up our tables, get this expression, evaluate it for our particular time of KT at this stage, so KT, and then use your transfer table, just follow through that process, and then we can evaluate it for our particular specific time, not our KT time, which is the general time, but for our specific sampling time of 0.5. Now remember, we can have different sampling times. So the point of the matter is that it's why I do this all the way through to here is because that way we have a general solution, and always work to a general solution. I'll be looking for that in all solutions, so work to a general solution and then plug in your values finally. So in this case, we're going to now evaluate what happens at our sampling interval or sampling rate or time interval of 0.5, plug in our numbers. Okay, again, there's always work to 4 decimal places. Go through, and we want to make sure we have the simplest form. So therefore then, here we have our, remember we're finding G2 of Z evaluated at T equals 0.5. So when we do that, we end up with this expression. Then we've got to go and substitute that back in, because overall we're trying to find G of Z, if you remember. Plug that back in. When you do that, oh look, you'll find a lot of times that this Z minus 1 term will drop out. So ultimately do some simplification, and pretty much that's what we're looking for. We're looking for the Z transform. So we've solved our problem basically. And again, mathematically, this is in its simplest form. So the major outcome of the discussion and the example is that we've demonstrated that once the pulse transfer function G of Z of a system is obtained, then the transform of the sampled output response C of Z for a given sample input can be evaluated using that relationship. Now finally, the time function can be found by taking the inverse Z transform, although in reality we have stopped at the beginning and basically just done that G of Z as we've done here. But I just wanted to remind you that pretty much you can do that. We haven't done that in this example, but keep in mind that could be an assignment question or a tube question, or it may not be a question at all, but or in your other practices you might have to do that. So the key thing is that keep in mind that we've been able to find this part of the expression, the G of Z, and then you can do other things too to find the C of Z, etc., etc. But we've just concentrated on G of Z. All right. So again, from mathematical modeling of electrical systems using the fundamental electrical principles, circuit analysis through to Kirchhoff's laws, through to Ohm's laws, for mechanical systems, looking at friction, damping, inertial masses, all those fundamental things come into practice, rotational things as well. And ultimately what we're trying to do is try and find the transfer function.